Hey everyone, and welcome. If you're getting ready for your IGCSE chemistry exam, you probably know that the paper 6 planning question can be, well, pretty intimidating. They ask you to design a whole experiment from scratch, and that's a lot to handle under pressure. But seriously, don't worry. Today we're going to break down a simple, repeatable strategy that will make these questions totally manageable. So here's our game plan. First, we'll get to the bottom of what makes these paper 6 questions so tricky. Then, I'm going to walk you through a 4-step plan you can literally use for any question they throw at you. We'll put that plan to the test with 2 different case studies, one on solubility and another on temperature changes. And we'll wrap it all up with a final checklist to make sure you lock in those top marks. All right, so first things first, let's get real about why these questions can feel so tough. For a lot of students, planning an investigation is easily the hardest part of paper 6. You know, it's one thing to answer questions about an experiment someone else designed, but it's a whole other ballgame to create one yourself.
And that really is the big question, isn't it? It can definitely cause a little bit of panic in an exam. You're just staring at a blank page, and you've got to come up with this logical, scientific, step-by-step method. But what if I told you there was a structure, a framework you could follow every single time, no matter what the experiment is about?
Well, that's exactly where our 4-step plan comes in. I want you to think of this as your secret weapon for any paper 6 planning question. It's your roadmap to a great answer. So here it is, the 4-step framework, and it's incredibly powerful. First, you identify. Pinpoint the method and all the equipment you're going to need. Second, you explain. You lay out your method step by step, and this is absolutely crucial. You have to mention your control variables. You know, all the things you're keeping the same to make it a fair test. Third, and don't ever forget this one, you state that you will repeat the experiment to make sure your results are reliable. And finally, number 4, you analyze. You explain exactly how you'll process your results to get to the final conclusion. That's it. That's the whole blueprint. Okay, enough talk. Theory is great, but let's see this plan in action. We're going to apply our brand new framework to a real exam-style question about finding the solubility of a salt. So, here's a typical task you might see. Plan an investigation to determine the solubility of magnesium sulfate in water at 50 degrees Celsius. Basically, our job is to figure out just how many grams of this salt can dissolve in 100 cubic centimeters of water at that very specific temperature. Using our framework, the first thing we do is identify the key variables we need to control. What has to stay the same for this to be a fair test? Well, the question tells us the temperature has to be locked in at 50 degrees Celsius, and we also need to use a set volume of water. Let's go with 100 cubic centimeters. These are our main control variables. Now for the explain step, our procedure. First, we'll use a burette to measure out the water because it's much more precise than a measuring cylinder. Second, we'll use an electrical water bath to keep that temperature at a constant 50 degrees, way more reliable than a Bunsen burner. Third, we weigh an initial amount of our salt that we know is more than enough. We'll call that mass M1. Fourth, we add that salt to the warm water and stir and keep stirring until the solution is saturated. That means no more can possibly dissolve. Fifth, we filter out all that leftover undissolved solid and we weigh it. That's our mass M2. And of course, for the repeat step, we clearly state that we'll do this whole thing at least 2 more times so we can calculate a reliable average. And for the grand finale, the analysis. How do we get our final answer? It's actually a pretty simple calculation. The mass of salt that actually dissolved, let's call it M3, is just our starting mass, M1, minus the leftover mass, M2. That final number, M3, is our solubility in grams per 100 cubic centimeters of water. And just like that, we've nailed all 4 steps. All right, ready for round 2? Let's see how our framework holds up when we get a question that asks us to compare 2 different things. We'll look at a case study that involves 2 different chemical reactions. Okay, here's our task. We have 2 reactions that both get colder when they happen. We call them endothermic. Our job is to design an experiment to figure out which one causes a bigger drop in temperature. This is a classic comparison investigation. First up, let's identify our control variables. To make this a fair comparison, a fair race, we have to use the exact same mass of sodium hydrogen carbonate for both experiments. We also need to use the same volume and the same concentration of both the acids. And one more thing, to stop heat from escaping and messing up our results, we'll do the whole thing in polystyrene cups. They're great insulators. So, what's our procedure this time? First, we'll measure the hydrochloric acid into our insulated cup and take its starting temperature. We'll call that T1. Then we add our pre-weighed solid, give it a good stir, and watch that thermometer very carefully. We're looking for the lowest temperature it reaches, and that's T2. The total temperature change, or delta T, is just T1 minus T2. Then what do? We repeat the entire process, but this time we use ethanoic acid instead of hydrochloric. And for our final analysis step, we just compare the results. We take the temperature change from the first reaction, delta T1, and we put it side by side with the temperature change from the second reaction, delta T2. Whichever reaction has the bigger value for delta T is the one that caused the larger temperature drop. That means it's the more endothermic reaction. Simple as that. Okay, to bring it all home, let's go over the absolute must-haves for your answer to get those top marks. I want you to think of this as your final mental check before you move on to the next question in the exam. Think of this as a quick scan you do in your head. Ask yourself, did I explicitly say I'm going to repeat the experiment and take an average? Have I listed all the important control variables? Did I name the right, most precise piece of equipment for the job, like a burette instead of just a beaker? And if it's relevant, did I mention a simple safety step, like wearing safety goggles? Taking these boxes is how you maximize your marks. So there you have it. You've got a solid framework and a clear checklist. You're not just going into that exam hoping for the best anymore. You have a real, concrete strategy to attack these planning questions with total confidence. You really do have the tools now. Go ace that exam. Fundoo Tutor is a personalized learning platform that helps students succeed in Cambridge, IB, and other international curriculums with expert mentorship, structured learning support, and engaging resources.